Hello and very welcome back again. So we are continuing our discussion on the Verilog, which is a hardware description language to model and describe your components in the digital electronics so that you can actually design variety of circuits. Okay. So in our previous module, we talked with the examples of using Verilog for the data flow modeling. For example, you see these codes that we covered in a previous model, and if we are given this expression E equals to A or B and C or B bar and D and this one also, so we can use these kind of Verilog modeling syntax. So what you do, you start with the module, then name of the module. In my case, I have given the name simple underscore circuit. You can write it example one or whatever, and then put the parenthesis, and in between these two parentheses you define your output port and the input port. So I have defined these output ports, which are E and F are my output variables, and A, B, C, D are my input variables. As you can see in our previous model, we said A, B, C, D are my inputs and E and F are my outputs, and accordingly I have to write a code for this Boolean expression E equals to and F equals to. So then I put the semicolon, and after that I use these statements. These are called as continuous assignment. So the syntax for that: assign E equals to this expression, the first one that I have written here, and the second expression for F, assign F equal to this expression. So we told you about this in our previous model. So if you are new here, coming here for the first time, you are encouraged to refer back to those previous model, and then finally we end the module. Okay, so this is a very simple code that we use to describe our digital equation. So that's kind of modeling technique is called as data flow modeling. Data flow in the sense we are just telling in the through the Boolean expressions how the data is being transferred from input to the output. There is this one, a little modification of this code here. So you see that I have written the module simple underscore circuit. In the parenthesis, I have defined all outputs and input, and then outputs here, inputs here, and there is no parenthesis here. So that's it. But assign statements like here, they are the same. And finally, I write the end module. Okay, so this is one way you can define your equations, the Boolean expressions, that is called as data flow modeling. What about there is another technique or another modeling method in Verilog that we will see now. So this is called as structural modeling technique or gate level modeling technique. So in this kind of modeling technique, what you use the inbuilt primitives in the Verilog. So primitives in the sense there are inbuilt components. For example, the logic gates, AND gate, OR gate, NOT gate, and so many other gates. So you see here AND, NAND, OR, NOR, XOR, and XNOR. So buffer, you know what is the buffer here. So buffer is a simple gate that transfer input to the output. Then you have a NOT gate. Then you have this buff IFO, buff IF1. So these are called as tri-state buffers. So in this case, when your control signal is 0, then your output gets connected to the input. So let me write here and explain you that. So you see that this one would be modeled like this. I mean, the component looks like this. So here you have the input, and then here you have the output, and this is your control signal. This is your control. So when your control is 0, then input gets transferred to the output. Okay. But in this case, if your control is 1, then the input gets transferred to the output. Okay. In this case, NOT, not IFO and not IF1, you have the tri-state buffer again, but Okay, let me correct it. You have the tri-state buffer again, but in this case, when your control is equal to 1, then your input gets transferred to the output. Or in this case, when your control is equal to 0, when the input is connected, then the input gets connected to the output. So this is how you actually can see these inbuilt primitives are quite useful in the Verilog, and we can use them directly. So they are multi-input primitives. It means they can have one input, two inputs, three inputs, and number of inputs. So for example, if you want to use AND gate as a primitive, so you will say that I have this AND gate, and this has number one input, number two input like this, and up to n number of inputs I can have, and this is your output here. Okay. So this is how you see that there are multiple inputs primitives available, and you can use them directly. So for example, look at this gate. I have used AND gate, which is two input. I have get NOT gate, which is one input. Obviously, NOT gate has a one input here. And there is a OR gate which has got two inputs. So the inputs to this OR gates is the output of the first AND gate, which is coming here, and you have defined here is the internal connection as W1, that is a wire 1. And there are two outputs of this circuit, D and E. So if I ask you to write a Verilog code for this, as I said and explained to you before, you have the very first option of describing this circuit using the data flow modeling. What you will do here, you know that by means of logical expression, with your knowledge of digital electronics, you know that output expression, Boolean equation for D output would be W1, obviously, uh, or or you would say the output is E here, that is E. Okay, so if you see that you explain W1, that is a wire 1, is actually A and B, okay, or E is equal to C bar. Okay, so this is how you got the first expression. What about the E? E is equal to simple C bar. So you see that the expression for D is this, and expression for E is this one. So I will ask you to write the code for this, and you will go back to the previous circuit right here. Let me clear the drawing so that you can understand. You will say module simple circuit in the parentheses with the semicolon. You will say outputs are D and E, and inputs are your A, B, and C. And then you will use these assign statements, just what you have used here. You will say output D is equal to what, and output E is equal to what. So you will use those digital logic equations, the Boolean expressions that we just written here. Okay. So that is your data flow modeling technique. But there is one another technique that is called as structural modeling technique that we are going to explain. So if you want to write the code using the gate level modeling, I am going to tell you this code now. Okay, so have a look at this, how we will do that. So what you do here, okay, so before I explain you how to start writing the code, let us have the example that is shown right here. So you see there are three gates, and on each gate we have written something. So this is gate number 1, G1, and it has got a delay, which is called as propagation delay of 30 nanosecond. So in a practical circuit, each of these components will have their inherent propagation delay. What is propagation delay? Is the amount of time that that is it is the amount of time to reflect the change in the output due to the changes in the input. I repeat again, the propagation delay is the time taken to reflect the changes in the output due to the changes in the input. So when you have a change in the input, there will be some 10 nanosecond here to reflect the change in the output right here. Okay, so the each gate, each practical circuits, they will have that is there due to the parasitics inside the logic gates, which are made of using transistors and all that. So there is a capacitor, resistance, and everything there. So because of the parasitics, each gate has uh, inherent propagation delay. So here is the 30 nanosecond, here is 20 nanosecond, here is 10 nanosecond, and you want to take into account them while you write the code. Okay, so here the first command that you start with in the bracket, I have seen that there is a time scale of 1 nanosecond. So the propagation delay is expressed in nanoseconds per picosecond. So there is a resolution. This 1 picosecond is the resolution, and the propagation delays are expressed in nanoseconds. So these are the comments, time units. I have defined it in the nanosecond, and then resolution is in the picosecond. Then I will start with, okay, module, and the name of my module is and underscore or underscore propagation underscore delay. I can give any name, for example, simple circuit, for example, or and or logic, whatever. Then I use the two parentheses, opening bracket and the closing bracket, followed by the semicolon, and in between I will define the input and the output. Okay, so inputs of my circuits are ABC, outputs are D and E. So that's it. So then I will close these with the semicolons right here. Then obviously I have one internal connection, that is a wire 1, and I will write wire W1. And now look at this. I can have an option of using these assign statements and then write D equal to what and E equal to what. So this is the data flow modeling. Instead, I am using the gate level modeling. So I will use the inbuilt Verilog primitives, directly call them. That is allowing me to model combinational circuit. I can make bigger circuit also out of these primitives. Okay, so how to write and call those primitives in a Verilog? I will write direct and. So I will use these names, and I have and gate, then I have a or gate, and I have a not gate. So I have used and, not, and or. So you see that I can call them in any order. I can call or first, I can call not first, whatever, and they will, that is possible because these three commands will be executed concurrently. When you perform the simulation, the order of specifying those primitives doesn't matter. Okay, so how to write this? And G1, so that is the gate 1, and now I introduce this is hashtag 30. That means the gate has a propagation delay of 30 nanosecond, and in bracket then I define the outputs and the inputs of it. Now remember, output, which is W1 in this case, must be defined or declared before the inputs. So output will always be first here, and then it will be followed by the inputs. So A, B are the inputs. Here also for the NOT gate, the delay of 10 nanosecond in bracket, output first, which is E, and the input, which is C right here. And finally, OR gate G3, 20 nanosecond delay, D is the output right here, and W1 and E are the inputs to these OR gates. So propagation delays are mentioned. Finally, end module. So this is how you actually have written the gate level modeling, the Verilog code using gate level modeling to describe your hardware. So the advantage of using Verilog primitives is that they allow you to direct model of a combinational circuit. Okay, and you can make bigger and bigger circuits. Okay, these gates can be listed in any order. So hope you found this video useful, in which you understood the comparison between, or the difference between, data flow modeling and the structural or gate level modeling. There is one more technique that is called as behavioral modeling that we will cover in some other modules. Okay, so if you like this module, share it with others. Stay tuned for more engaging content like this, and we will continue our discussions in understanding Verilog very soon. So wish you happy learning.